Let's look at related rates today. The basic premise behind related rates is that if you have quantities whose variables are related, then so will their rates of change also be related. And we're going to do some examples today in this lesson, and I'd rather just jump into the kind of the how-to and show you how to do these problems rather than get philosophical or try to over-explain it up front. So let's go through the steps somewhat quickly. Of course, with any problem, you should read the problem carefully. You should make a sketch and try to identify what is given and what we need to determine. That'll be very important, especially when we try to identify what the rates are. You're going to look for phrases like at a rate of. It's going to tell you how fast something is moving, or it's moving with respect to time, and it's going to identify it as the way something changes over time, or dx dt, that kind of thing. The next thing you want to do is identify the equation and write it out. What's expressing the basic relationship? Is it the area of a circle? Is it the volume of a sphere? Is it the Pythagorean theorem? Is it sine of theta equals opposite over hypotenuse? Whatever that is, we're going to write it down. Once you have the equation written down, we're going to differentiate the equation with respect to time. And that's going to tell you everything you need to know, because after that, it just becomes an algebra problem. So once we have that, we're going to substitute our known values from step number 1, and we're going to solve for what we're looking for, also from step 1. And the last one is just a test of reasonability. Are the units good? Is the answer reasonable? And the most common mistake that we see here is usually a sign issue, like a plus or a minus. Generally speaking, if the quantity is getting smaller, it should have a negative rate of change. If the quantity is getting larger, it should have a positive rate of change. So let's just jump in and see what we can do with example 1. Example 1 deals with an oil rig and has sprung a leak, and it is fanning out oil in a circular pattern. It says here, if the radius of the oil patch increases at a rate of, remember that phrasing from before, the radius is increasing at a rate of 30 miles per hour. They're telling us that dr dt is 30. The radius is increasing by 30 meters per hour. The follow-up question is, how fast is the area of the patch increasing? That's the unknown. They want to know what is dA dt. Well, I don't know, but we'll find out. And I guess the other finally is when the patch has a radius of 100 meters. Well, they're not giving you a rate. Now they're telling you that the radius is literally 100 meters. If you haven't guessed by now, the equation that relates A and R when we're dealing with a circle is A equals pi r squared. If we're going strictly by the steps, we've already done step 1 and step 2. Right? We've got that equation. Step 3 is just to take the derivative of this equation with respect to time. So if we do that, the derivative of A is 1 with respect to A, but because it's implicit differentiation, it has to get a dA dt tag attached to the 1. The pi is a constant multiple, and the derivative of r squared with respect to r is 2r, and because it's implicit, it gets a dr dt tag as well. All right, we've got our equation. Step number 4 reminds us to substitute the known values. Well, I've got dr dt is 30. I have r is 100. And I have pi. I'm going to rewrite that if you don't mind. I'm just going to go from the left here. We have equals, or dA dt is what I don't know. This equals pi times 2 times r, which is 100, over or times 30. And if you multiply this all out, you get 6,000 pi. Now, what's the appropriate unit? Here, r has a unit of meters. dr dt has a rate of meters per hour. And if you multiplied them literally, you'd get square meters per hour, which I invite you to do. You can do this very literally and just take the units and multiply them together or divide, whatever the case may be. However, we know that it's an area problem, so it's a circle. And the circle has an area at this point, or it's increasing at a rate of 6,000 square meters every hour. Sometimes common sense will win the day, and you can do it however you want. But just that step 5, like, does everything make sense? 6,000 pi square meters, okay, it's positive, so the circle is growing. And square meters per hour seems like a reasonable unit. If not, I'd go back and check for mistakes. We'll look at example 2. In example 2, we have 2 small planes approaching an airport. One is flying due west. We're going to call this the airport here. One of the planes is flying due west toward the airport at 120 miles per hour. So I ask you, is the distance to the airport getting smaller or longer? Shorter or longer, excuse me. It's getting shorter. The pilot is approaching the airport. So dx dt, the way that x is changing over time, at that moment, it's decreasing by 120 miles per hour. There's another pilot approaching the airport going due north, and this pilot's rate of change is 150 miles per hour. So we know that dy dt is negative 150 miles per hour. I kind of left out that I made the horizontal unit x and the vertical unit y. All right, so I'll put a different color. This is x and this is y. Therefore, that's dx dt, negative 120. This is dy dt, negative 150. Okay, so we've taken care of a lot of this. It says, how fast is the distance between the planes changing? This implies that there's some third distance here. So at this particular moment, we have this distance called z. And z is changing. If you can imagine 5 minutes into the future, the planes will be closer, and z is also changing at that time as well. So the problem is asking us for how fast is the distance between the planes changing. This wants to know what is dz dt. When the westbound plane is 180 miles from the airport, and the northbound plane is 225 miles away from the airport. So the question is, what equation relates these 3 quantities, x, y, and z? We have a very large right triangle, and we're talking about distances. To me, this says we're dealing with the Pythagorean theorem. So there's my equation. All we've done so far is kind of make the diagram, figure out what we know, what we don't know, and now it's time to differentiate. So I'll take the derivative with respect to time, and I'm going to get derivative of x squared is 2x dx dt. Just as a kind of time saver, I'm going to replace dx dt with x prime. The derivative for y squared is 2y times y prime, and the derivative for z squared is 2z times z prime. Now, one thing I like to do with these Pythagorean problems is everything here is divisible by 2. I'm just going to knock out the 2's from all 3 terms. Many people don't do this. I just find it to be a little bit easier as we go along. Let's fill in what we know. All right, here we go. We have x equals 180. We have x prime is negative 120. Plus, we have y is 225. We have y prime is negative 150. We don't have z, but I can figure out z, right? Z I can get by Pythagorean theorem, right? So z squared equals x squared plus y squared. So z should be the square root of 180 squared plus 225 squared. So let's take a look at that on the calculator. I've already done this actually. Let me go up here. Yeah, I've already done this. So I'm going to retype it. It's the square root of 180 squared plus 225 squared. And that's 288.1. 288.1. So that's my value for z. And I still need z prime. All right, so z prime is simply all of this information on the left divided by 288.1. I'll put the answer over here to the left. Let's see here. All right, so we have, right, I just did divided both sides by 288.1. And I'm going to go back to my calculator. And let's see what we have here. We have 180 times negative 120 plus 225 times negative 150 all over 288.1. And this gives us negative 192.1. Negative 192.1. And that's z prime. Negative 192.1. It's going to have the same unit as dx dt and dy dt. It's miles per hour. So that is our rate of change. That's how quickly the planes are changing. The distance between the two planes is changing at that moment. Now, at different points in time, it will be different. But at that moment in time, that snapshot, we're looking at 192.1 miles per hour, getting closer together. The distance between the planes is shrinking. Examples 3 and 4 are a little more conceptual, but definitely doable. Let's jump in. Here in example 3, we have coffee draining out of a conical filter at a rate of 2.25 cubic inches per minute. So we have a filter, a coffee filter in the shape of a cone, and coffee is pouring out of it at a rate of 2.25 inches or cubic inches per minute. Now the coffee filter is losing coffee. It's being poured out. So it's a negative, the volume is changing at a negative rate. It's losing coffee. Now, what else do we know? That's dv dt. We also know that the cone is 5 inches tall and has a radius of 2 inches. Right? So the height is 5 and the radius is 2. This is important for the setup, but it's not important for the final answer. We'll talk about that in a minute. How fast is the coffee level dropping? Now, what is that asking for? How fast is the coffee level dropping? It's not how fast is the coffee coming out. It's how fast is this level changing, the height. So the problem wants to know, tell me about dH dt when the coffee is 3 inches deep. So the height is 3. So these are my important numbers for the setup of the problem. I'm going to explain why did they give us this information. If you can imagine this cone, we've already explained it's got a height of 5 and a radius of 2. I'm not going to write those numbers, but I'm going to establish that's 5 and 2. Now, as the coffee flows out, it is now flowed down to the point where the coffee is now 3 inches high in the cup or in the filter. So can you see that that creates a similar triangle? This red triangle is similar to the triangle in black, the original triangle. So what we have here is the ratio of the radius to the height is 2 to 5, which implies that the radius is 2/5 of the height. So now when h equals 3, I have a way of figuring this problem out. I'll explain more in a second, we are being asked to figure out a relationship between volume as it compares to the height. Now, the formula we know from geometry is that the volume is 1/3 times pi r squared times the height. Taking the derivative of this involves the product rule, which is not so bad, but when you take the product rule with implicit, we'd end up with a dr dt and a dh dt, and the bookkeeping starts to get a little out of hand. Well, the good news is we already figured out a way to replace r with the variable h. Let's do that below. Volume is 1/3 times pi times 2/5 h quantity squared times h. And if we apply a quick cleanup to this, that's 1/3 pi times 4/25 h squared times h, or finally, that is altogether 4 pi over 75 h to the third. There's a volume formula that depends only on the height of the cone. If I now take the derivative like we're supposed to, I get dv dt equals 4 pi over 75 times 3h squared dh dt. We're doing great. All we have to do now is solve for dh dt when we know all the other stuff in the problem. I think what I'm going to do is one more cleanup step here. We're going to do dv dt equals, I'm going to cancel the 3 and the 75 to 1 and 25. So we're going to get 4 pi over 25 h squared dh dt. Let's plug in what we know. That dv dt is negative 2.25. I'm going to leave 4 pi over 25 as a constant. H squared, 3 squared, that's 9 times dh dt. I'm going to keep this as calculator ready as I can. I'm going to go negative 2.25 equals 36 pi over 25 times dh dt. So I can finally say dh dt is negative 2.25 times 25 over 36 pi. And what does that look like? Let's find out. Negative 2.25 times 25 over 36 pi. According to my online calculator, as you can see, that's negative 0.497 inches per minute. Now, why did I know it was inches per minute? Because the volume was measured in cubic inches per minute, and height is simply a linear measure, right? It's just a linear measure up and down. So one-dimensional, inches per minute. Definitely a harder problem. You get better with practice. We'll have plenty of opportunities to practice these as we go along. Let's look at this one last video here. One last example, rather. We're observing a launch. An observer stands 200 meters from the launch of a hot air balloon at an elevation equal to the elevation of the launch site. All they're saying is the observer is on a flat level from where the balloon is being lifted. So the observer is 200 meters away. The hot air balloon is being launched. And what else do we know? The balloon rises vertically. Shall we call this y? So they're telling us dy dt equals 4. Read that one more time. 200 meters from the launch site, hot air balloon equal to the elevation. The balloon rises vertically at a constant rate of 4 meters per second. How fast is the angle of elevation of the balloon increasing 30 seconds after the launch? This is my angle of elevation, theta. How fast is it changing? So the question becomes, what is an appropriate equation that relates these quantities? What relates theta, what relates theta and the opposite side and the adjacent side? It's not Pythagorean theorem. That doesn't involve angles. It must be, let's see, SOHCAHTOA, opposite and adjacent. It must be the tangent. So the tangent of theta equals y over 200. That's my equation. Now, what we want to do is take the derivative of both sides with respect to time. The derivative for tangent of theta is secant squared of theta. But theta is not t, so it must get a d theta dt. Good news, that's what we're looking for. It says how fast, right? It says how fast is the angle of elevation of the balloon increasing. That's this. Good. So we have secant squared theta d theta dt equals the derivative of y over 200. Remember, y over 200 is the same as 1 over 200 times y. That's a constant multiple. So I can just say that that derivative is 1 over 200 times y prime, or rather, excuse me, I'll say dy dt. I'll say dy dt, which we know is 4, right? So what do we have here? This is what we have. This is our equation. Secant squared theta d theta dt equals 1 over 200 dy dt. We want to solve for d theta dt. So how would you do that? Well, I want to get rid of the secant squared. I guess I could divide by secant squared. Let's see, let's do that. So d theta dt equals 1 over 200 secant squared theta times, I'll put the dy dt here in the top because it's being multiplied. So isn't that just equal to dy dt times cosine squared theta over 200? And don't I know what dy dt is? Dy dt is 4. All I need to know is, what is the cosine of theta? What is the cosine of theta? Well, my angle is, I'll do it in blue, my angle is here. What is the cosine of that angle? Well, cosine is the adjacent over hypotenuse. So it's definitely 200, but what's the hypotenuse? Well, this raises an important question, because 30 seconds after the launch, if this is rising at a constant rate of 4 meters per second, what's the value of y? Shouldn't that be 120 feet, or meters rather? Right? 30 seconds of travel at 4 meters per second would make this 120. So the hypotenuse, or the actual distance, is going to be the square root of a squared plus b squared. Let me move over here to my calculator, and let's do the square root of 200 squared plus 120 squared, and that's about 233.2. I'm going to keep it at that number, 233.2. Let's write that down. So 233.2 is d. So what's the cosine? Well, it is 233, excuse me, it's not that. It's the adjacent over the hypotenuse. It's 200 over 233.2. And I'm going to quickly do that on the calculator again. Let's pull that up. So 200 over the previous answer is about, I'm going to go 0.857. That's the cosine. About 0.857, and I want to square that, right? Let's see. 0.857 squared. Whatever I get here is my answer. So let's work this out on the calculator one last time. I'm going to square that number. So previous answer squared times 4 over 200. And I get that the angle is increasing at about 0.015. What's the unit though? 0, so I get 0.015. Well, the angle of elevation is measured in radians. And our unit of time is seconds. And that is how quickly the angle of elevation is changing at that moment in time. So you can see the range of difficulty that comes into play. Some of them are very easy and others are more intricate. So I'm hoping that by practicing these on your own and getting better at these, they'll just become second nature. The good news is the steps are always the same. So good luck trying these, and if you have any questions, leave something in the comments and I'll be happy to get back to you. Good luck.